Hello, can you all hear me?
Yes, ma'am.
Okay. So, good morning. Welcome to lecture 23 of our CS2 classes. And yesterday, I think while I was still saying a couple of things, I realized that I wasn't being recorded. So, let me just go through that again. Okay, so yesterday we looked at, if we have a ARP process, we know that it is never going to be a Markov process until and unless that P takes a value which is 1. So we figured out a way to convert any ARP process into a VAR1 process by writing it in such a manner. So just to remind you guys, when I say VAR model, I have vectors here. So vector autoregressive model. So instead of just one random variable, I have a set of random variables here, and it can be different or it can be the same as well. But at the end, what you do is you define that one vector as WT, and then you have its lagged value on which these WT are depending now. So you can see that WT depends only on WT minus 1. And now we can say that this is a vector autoregressive model of order 1. And then similar thing you can do with the AR3 model and so with the ARP models as well. But now what we have is sometimes we don't only have an AR model, we can have a model which is not stationary initially. But then you have to differentiate it once, twice, or thrice to make it into a stationary model. But the same problem will possess here as well. As long as your P plus D is greater than 1, this ARIMA does not follow the Markov property. But again, vector autoregressive models will come to our rescue, and then you can define YT as xt minus 1 up until xt minus P plus D minus 1. So remember what we did here was, I had written T minus P minus 1, right? Which will just be T minus P plus 1. And this will just be X T minus P minus D plus 1. So just to compare, let us say I'm looking at my AR3 process, right? So what I have here is xt minus 1 and xt minus 2, right? And I'm looking at AR3 process. So this is my P and 2 is just P minus 1. So which is 3 minus 1 equal to 2, and you have a T here. So that is how you get this T minus P plus 1. And that is the same reason you will get something like this. So you will have xt minus P minus T minus 1. And now we try to look at what happens if I add a Markov process. So let us say I have an ARIMA P comma D comma Q. For any Q greater than 1 will never be a Markov. In fact, not only greater than 1, but greater than or equal to 1. Can anyone say me why could this be the reason that, any MA model that you have will never be a Markov process? Can anyone tell me why could that be the case? So let us see how is that possible. Let me now, for example, just take an ARIMA 1, 0, 1. So if I write the model for this, it will be something like xn plus 1 equal to alpha times xn plus en plus beta en minus 1. Oops. right? It would be this model here. So what I am saying is that if my model has to follow a Markov property, I know that my xn should only be dependent on xn minus 1. No information about xn minus 2 should anyway alter the value that I derive of xn on the basis of xn minus 1. But here if you have a look, so the only term that has been added because of this MA is this E, sorry. So it is this En minus 1, right? So if you have a look there, what happens is once you, so let's say you know the value of xn minus 1 and you know En as well. So still you cannot define what will be the value of xn. You will have to figure out the value of En minus 1, which in turns depends not only on xn minus 1 but also on xn minus 2. And that is the whole reason why whenever you have a look at the MA processes, they don't generally, satisfy the Markov property. Now let me have a look at an example as well. So for now, let us even exclude this AR term that we are looking at. I only have xn equal to En plus beta En minus 1. So let us ignore the beta term as well. Let's just keep it very simple. So now I'm looking at this process where it is just a MA1 process, right? And I say that my En follows normal 0, 1 process. So now if I see, let's say if I write my xn minus 1, it will take the value En minus 1 plus En minus 2, and xn minus 2 will take the value En minus 2 plus En minus 3. So now let us say I want to figure out my value for xn and I'm checking whether this process is a Markov or not. So I know my value for xn minus 1. Let us say that it takes some value. Let us say that it takes some value which is equal to 0. So now I know that my En minus 1 is going to be equal to the negative of whatever value my En minus 2 will take, right? And I know that to figure out my value of En minus 2, it in a way depends on xn minus 2 as well. And there is no other way to know the value of En minus 2. So if xn minus 2 is, more likely to be a higher positive number, so is En minus 2. And if this is a highly positive number, then because we have a negative here, then this is going to be a nice negative number as well. And this will clearly impact here. And if this is a bigger negative number, then there will be a dampening effect on the value of xn that we're trying to figure out. So you see that because of the presence of first lagged value of E, you cannot say that this xn follows a Markov property. Now, let me show you a concrete example of, how is that the case. So we'll try to solve a question. So I have a xn which is equal to En plus En minus 2. And I can easily see that this is a MA2 process, right? And I see that my En follows normal distribution with mean 0 and variance 1. So the first thing that we have to do is figure out the chance that my xn takes a value greater than or equal to 0 such that xn minus 1 takes a value less than or equal to 0. So how should I go about solving this? Anyone?
We can put in the values of xn and xn minus 1.
Yeah, we can put in the value of xn and xn minus 1. Let us see what happens then. So I put xn as en plus en minus 2 greater than or equal to 0, given that en minus 1 minus en minus 3 is greater than or equal to 0. So what should be my next step? So now I can easily see that the things that I'm conditioning upon is n minus 1 and n minus 3. And what I'm looking for is n plus n minus 2. So I know that my n minus 1 and n minus 3 are clearly independent of the values that my en and en minus 2 will take, right? So I can just carry this forward as it is. I will have en plus en minus 2 greater than or equal to 0 here. And I know that my en follows a normal 0, 1. So if my en follows a normal 0, 1 and such is my en minus 2, then my expectation of en plus en minus 2 will be 0 and my variance of en plus en minus 2 will be 2, and I can see that this sum follows a normal distribution with mean 0 and variance is 2. So this again follows a normal distribution, which means it is a symmetric distribution. So if I say that 0 is here, I know that 0.5% of the points are going to lie here. Sorry, 0.50% of the points are going to lie on the left hand side. And when I'm talking about the probability that en plus en minus 2 takes a value greater than or equal to 0, I know that I'm talking about the other half, right? Which will give me a chance of again 0.50%. So that's good. And now let us see if this remains the same. If this value still remains the same, if I am asked yeah, so I am looking at the probability that my xn takes a value greater than 0, given that xn minus 1 is less than or equal to 0. So this is as it is from the previous case, but now we are given additional information about xn minus 2, which is again less than or equal to 0. And now we are trying to figure out what will happen to the answer. So I know that if my answer for xn greater than or equal to 0 still remains the same, that is, if I can see that 50% of the times my xn will take a value which is higher than 0, also given that xn minus 2 takes a value less than or equal to 0, then I can see that this xn is a Markov process. But let's see what happens. So we know that this is a ML2 process and it shouldn't hold Markov, but this is just a nice exercise to see and get a nice intuition of why does ML processes do not follow Markov property. So if I were to write this in probability terms and expanding this xn's, what I will get is en plus en minus 2 being greater than or equal to 0, given that en minus 1 plus en minus 3 is less than or equal to 0, comma en minus 2 plus en minus 4 is less than or equal to 0. So now we know that even though en and en minus 2 do not in any way depend on n minus 1 and n minus 3, they do depend on what the value of n minus 2 will be. So now we cannot eliminate all the conditionality that we have. So we will still have this, which I can write as such, right? So now what I'll just use the Bayesian formula that we always do. So I'll have a probability that En plus En minus 2 takes a value greater than or equal to 0, and that En minus 2 plus En minus 4 takes a value less than or equal to 0. And this will be conditioned upon this. The chance that En minus 2 plus En minus 4 takes a value less than or equal to 0. So I know that this is going to be same as this and that, because I'm looking at a normal distribution, which is a symmetric distribution, right? So this will just be 0.5. But how can we, figure out the numerator part of this? So this is going to just be 0.5. So let us try to see what happens in the numerator. So what I have is, we know that the process Xn will be Markov if and only if the probability if and only if these are equal, right? So if we look at what was the answer that we got here, it was something like 0.5. And for this, we just derived the whole numerator, which was something like this. We had a denominator which was something like 0.5. So I can remove this denominator and I can just multiply it here for me to get the value for this numerator as 0.25, right? So now we will minus 2, this should be true, right? So now let's see what happens if we figure out the numerator part of this. So now I have to look at this and I know what my value for this should be ideally. So what we can do is we can have an observation. So let us say we have observed the value of En minus 2. So we just say that so I'm saying that my En minus 2 has taken some particular value, which is this E. And now if I have to figure out the chance of this happening, how can I rewrite this in terms of E? So what I will have to do first is rearrange this whole thing into something which makes it more plausible for me to figure out the probability. So what I will do is I'll write En greater than or equal to En minus 2, and there will have to be a minus there, intersection En minus 4 being less than or equal to minus of En minus 2. And now I want this thing to be equal to 0.25. And I again know that all of my Ens just follow normal with 0,1. So I can use this assumption that I have made about my Ens, about my error terms, to calculate the chance of this event happening. So we have an end here, which means I'm going to multiply. So now this can be written as, so I have that En takes a value greater than or equal to minus of a some number. So I think what always helps me with this kind of situations is to draw this normal graph and see what part we are looking at, okay? So I'm looking at the chance that En is greater than minus En minus 2. So because I have a minus En minus 2, I know it's going to lie somewhere here. So I can write that my minus En minus 2 lies here. And let me say my En minus 2 lies there. So first probability is the fact that I get a En, I observe a En which is higher than this value. So when I'm talking about that part, I know I'm looking at this region, right? The chance that it takes a value greater than that. So now what I will do is I can rewrite this using the normal cumulative function. So what I have here is, again, now I'm looking at a greater than sign. So I can just rewrite this as 1 minus the chance that I'll observe something which is less than minus e. So this is nothing but minus of e, and this is nothing but e, right? So this I can rewrite as 1 minus the chance that I observe something which is less than this. And again, now I have this other part to look up to. So here it is asking me indeed the fact that I observe an error term which is less than or equal to minus of En minus 2. So I'm talking about this remaining part here, which I can just rewrite as this. And I see that this is equal to 0.25. So let me just do one more thing. And this is the remaining part here. Okay. And now we have a quadratic equation in terms of phi minus e, for which we know what value it should ideally take. So I solve for it and I will have an answer which is this. So you can easily see, right? 0.25 is the square of 0.5 and 1 minus 0.5 is just 0.5. If you multiply it by 0.5, it's going to give you 0.25. So I have my value for this as 0.5. Now, what does it mean when I say that, my phi of minus e is 0.5? I say that the probability that my error terms will lie below the value of minus e is 50%. And I know that my errors follow normal distribution. So I know that indeed my minus e is going to just be 0. So I know that my e, which is just e n minus 2, has to take a value which is 0 for this to be satisfied. So now I can probably draw a different graph here where I know exactly where my en minus 2 should be, right? And it is just going to be equal to 0. So now I know that process xn will be Markov. So we started off with, saying that the process xn will be Markov if this is equal to this. But I know that this is equal to this only when en minus 2 is equal to 0. Otherwise not. So you know that given some value of xn minus 2 has, in a way affected the way we are deriving our xn, we will know that en minus 2 has to be 0 for this to be satisfied, but that not for any en minus 2, this will be satisfied. So we know that in a way, this MA process, there is no way, for this MA process to become a stationary process. Is that clear to everyone?
Yes, ma'am.
Hello.
Yes.
Okay. Yeah. So I think that is the end of our first part of the time series chapter that we're looking at. And in the second chapter, what we have is more of an application type, So now we studied these models in detail. But when you go and, try to have a hands-on exercise with modeling this time series models within any software, what you will have is, first of all, some data set. And the only thing that you can do with that data set is to plot it initially to see how the and the best thing that you can do with that data set is to plot it initially to see how the thing that you're, the variable that you're trying to take into consideration behaves like. So let's have a look at of different time series. Yeah, so I have this 9 different time series where we'll try to figure out which one of them has much more chance of, being a stationary series. So where I'm talking about this series is just the stock price of the Google. So you see that, there is some trend within this. So let's say if I draw, I know that it is increasing over a period of time, right? So I'm looking at 200 consecutive days of the Google stock price. And here I have just taken the difference of the same series. And I know that this looks a bit random to me, right? I cannot necessarily see that there is something going on until and unless I look at some more statistic. And now let us look at this. So this is just the annual number of strikes in the US. And we see that it has, decreased and then it has decreased. So there is some trend going on, but not that persistent as well. But we see that, during the war times or the strikes, the number of strikes that we have gone up. So let us have a look at this graph. What do you guys think about this graph? So this graph is the graph which, denotes the monthly sales of the new houses being sold. So we see that there is some sort of a pattern to it, right? In some years, the monthly sales have clearly, so in particular months, we see that, the house sale increases. Okay, so let us look at this graph. You can easily see, even without knowing what this graph is, but this is just, the year-wise price of eggs, the year-wise price of a dozen eggs. So I know that this clearly has a downward trend. It is decreasing in nature. So even that is not going to be stationary. Oh, again, and when I talk about, some data being stationary, what do I mean? I mean that it does not follow any upward or downward trend. Rather, its mean and variance are consistent over the time. So there should be no seasonal effect and no other sort of effects on it. So now I'm looking at So now when I'm looking at this data, this is just the number of pigs that were slaughtered. So month-wise in each of this year. So I know that for some month, it clearly, has some pattern that in particular period, in some particular months, the number of pigs that were slaughtered increases, but then it again diminishes in later months. So I see that there is some seasonality going on there as well. We'll ignore this graph. And this graph here, again, you can see that there is some clear seasonality thing going on. And this trend And also, you see the variance it keeps on increasing over time. So here the variance is something like that, and here it was so less. So you see that the variance is clearly not stationary for this kind of data. So within all of these 8 graphs which is discussed, the only graph which is, trended upward. And for rest of the graphs, we saw that there is one or the other way in which the variables do, do not look stationary in the first place. So what you do is, given any data set, the very first step for you is to plot the data and see how it looks like. Because sometimes it could be as easy as looking at this data and just seeing that, okay, this is not stationary. So something needs to be done about this. Because we know that all the models that we have studied can only be used stationary process into a stationary process theoretically. And there are other ways as well. Like there are so many ways depending on the kind of trend or seasonality that you observe within the data to convert a non-stationary data into a stationary data, keeping the information that it is trying to convey and not distorting the information that let me discuss now a couple of techniques using, so let me just save this first. Okay, so now we'll discuss a couple of techniques using which we can detrain the data that we trained. I say that, hello, can you all hear me?
Yes, but it's
Yes.
breaking a little bit earlier. Can't hear you now.
Yeah, now you can.
Yeah, now it's on. Again, can't hear.
Can you hear me?
Little bit.
I think so. The internet's actually acting up again. So
Now I can hear you.
this, now you can hear me, okay? So
Yeah.
we'll see how this continues. Otherwise, I can, postpone the lecture to afternoon or evening sometime. Let's see. Yeah. So before going into seeing, how I can retrain my data, let us have another look at, deciding whether a model is stationary or not. So what you can do is you can plot the ACF. So these are my co-relograms. So this is for the stock price of the Google, and this is for the difference of that series. So remember, when I'm taking the difference of the stock price, my first data point here is going to be x2 minus x1. So you know that I will have one less data point whenever I'm looking at the difference series, but that doesn't, affect anything a lot. So here we see that this is 1. So because I know that the if there is a higher value, to my row 0. So row 0 will always be 1, and then you start with the next cases. Um, can you all hear me?
Yes.
Yeah, so I can see that in this graph, my ACF is decreasing slowly and steadily from 1, but it hasn't quite reached 0 yet. So I don't know that, so I do know that this model is not stationary in nature. But what we can do is, when you observe such cases, the very first thing that should come to your mind is to difference this series. If you take a difference for this series,
Can't hear you now.
can you hear me now?
Yes, now.